Have you ever stopped to really consider just how vast and mysterious our universe truly is? Out there, beyond the familiar planets and stars we see with the naked eye, lies a realm of extremes, places where the laws of physics are pushed to their absolute limits, where gravity is so intense it bends space and time, and where some of the most enigmatic objects known to science spin silently in the dark. Among these cosmic wonders, few are as puzzling or as powerful as neutron stars, the remnants of massive stars that went supernova, collapsed into incredibly dense spheres, and now drift through the farthest reaches of space. These aren't just distant points of light, they're nature's ultimate laboratories where matter is compressed to densities beyond imagination, and magnetic fields are trillions of times stronger than Earth. Today, we're setting off on a journey to explore 30 astonishing facts about these distant neutron stars, each one more mind-bending than the last. From their mind-boggling density, just a teaspoon of neutron star material would weigh as much as a mountain, to their incredible rotational speeds, some spinning hundreds of times per second. These cosmic powerhouses defy everything we thought we knew about the universe. We'll uncover how they form, what makes them tick, and why scientists are so captivated by their secrets. And as we venture into the depths of space, you'll discover how these distant objects are not just scientific curiosities, they're keys to understanding some of the biggest questions in astrophysics, from the nature of gravity to the origins of the elements that make up our world. So whether you're a seasoned space enthusiast or just curious about the wonders waiting beyond our solar system, this exploration is for you. We'll travel across light years, decode complex cosmic phenomena in simple terms, and reveal the breathtaking beauty and brutality of neutron stars. By the end, you'll see the night sky not as a static tapestry of stars, but as a dynamic, ever-changing universe filled with mysteries waiting to be uncovered. Ready to dive in? Let's begin. To truly grasp the sheer wonder of these distant cosmic powerhouses, we first need to understand what they are. Picture a star much larger and more massive than our own sun. After burning for millions of years, it doesn't just fade away. It ends its life in one of the most violent explosions in the entire cosmos, a supernova. This catastrophic event blasts the star's outer layers into space, creating those beautiful nebulae we often see in telescopes. But what's left behind is even more fascinating: the star's incredibly dense core. Without the outward pressure from nuclear fusion to support it, this core collapses under its own immense gravity, and I mean collapses. In less than a single second, an object that was originally hundreds of thousands of miles wide is crushed down into a sphere no bigger than a city, typically just about 12 miles across. Now try to wrap your head around what happens to the matter inside. The force of this collapse is so unimaginably powerful that it literally forces atoms to fuse together. Electrons are slammed into protons and they merge to become neutrons. This is where the name neutron star comes from. The entire object becomes a vast, ultra-dense sea of these subatomic particles, packed together tighter than anything else we know of in nature. This leads to their most famous, almost unbelievable property, their density. If you could somehow scoop up a single teaspoon of material from a neutron star, and that teaspoon would only hold about 5 milliliters, that tiny amount of stuff would not weigh a few grams. It wouldn't weigh a few tons, it would weigh billions of tons. To put that on a human scale, that one little teaspoon would have the same mass as a good-sized mountain here on Earth, like Mount Everest. It's a scale of density that simply doesn't exist anywhere in our everyday experience. This incredible density creates some of the most extreme conditions in the universe. The surface gravity is so intense that if you were to drop a marshmallow from just a meter above the surface, it would hit with the energy of 1,000 hydrogen bombs. And the landscape of a neutron star isn't like anything we know. Their crust is thought to be a crystalline lattice of atomic nuclei, but 100 billion times stronger than steel. It's a world where the mountains are only millimeters high because anything larger would be crushed flat by the overwhelming gravity. They are, in every sense, nature's ultimate physics experiment, showing us what matter is capable of when pushed to the absolute limit. But such an extraordinary object couldn't remain hidden forever. The story of how we actually found them is a fascinating tale of scientific prediction, serendipity, and a brilliant young researcher. The idea of a star made almost entirely of neutrons was first proposed back in the 1930s, just 2 years after the neutron itself was discovered. The brilliant and often controversial astronomers Walter Baade and Fritz Zwicky were the ones who put the theory forward. They were studying supernovae and correctly theorized that the colossal explosion wasn't the end of the story. They proposed that the collapsed core left behind would be an incredibly small, dense star composed of closely packed neutrons. At the time, it was a radical idea. Many in the scientific community thought the notion was just too outlandish to be true. For decades, neutron stars remained just that, a compelling but unproven theory, a ghost in the equations of astrophysics. That all changed in 1967 with a discovery that would revolutionize our understanding of the cosmos. A 24-year-old graduate student named Jocelyn Bell Burnell was helping to build a vast radio telescope in Cambridge, England, an array of wooden poles and wires covering an area the size of 57 tennis courts. She was meticulously analyzing the reams of data it produced when she noticed a tiny, curious signal. It was a series of rapid, precisely timed pulses, arriving exactly every 1.337 seconds. It was so regular that she and her supervisor jokingly dubbed it LGM for Little Green Men, half seriously wondering if they had stumbled upon a beacon from an alien civilization. But soon, Bell found several more of these pulsing sources in different parts of the sky, ruling out an extraterrestrial origin. What she had discovered was the first known pulsar, which we now know is a rapidly spinning neutron star. These objects have immensely powerful magnetic fields that funnel radiation into beams shooting out from their magnetic poles. If those poles are misaligned with the star's rotation axis, much like a lighthouse, those beams sweep across space. And if Earth happens to lie in the path of that sweeping beam, we see a pulse of radiation with every rotation, a cosmic lighthouse blinking in the darkness. Jocelyn Bell Burnell's incredible find was the first direct evidence that neutron stars were not just theoretical fantasies. They were real, physical objects out there in the universe. This discovery didn't just confirm a 30-year-old hypothesis. It flung open an entirely new window on the universe, giving astronomers a powerful new tool to study these most extreme and distant objects. Of course, the names given to these cosmic lighthouses can be just as fascinating as their physics. While the most famous ones, like the one at the heart of the Crab Nebula, might have evocative nicknames, the vast majority are identified by a long string of letters and numbers that might look like a random jumble at first glance. But there's a very precise method to this apparent madness. The most common prefix you'll see is PSR, which simply stands for pulsating source of radio. This is a direct nod to how they were first discovered through their radio wave emissions. The sequence that follows, like J1748-2446 AD, is actually a celestial address. It's based on the object's right ascension and declination, the longitude and latitude of the sky. The letter at the very beginning of that sequence, usually a J, tells astronomers which celestial coordinate system was used. A J means it's based on the J2000 epoch, a standardized astronomical reference frame for a specific point in time. So, while the name PSR J1748-2446 AD might sound complex, it's essentially a precise set of GPS coordinates that allows any astronomer in the world to immediately know where to point their telescope to find it. This one, by the way, holds the record for the fastest spinning pulsar we know of, and its formal name leads to its much cooler nickname, the Black Widow Pulsar. And that's where the nicknames come in, adding a layer of personality to these distant objects. The Black Widow pulsar earned its name because it's in a binary system and is actively vaporizing its companion star with its intense radiation, a rather sinister cosmic relationship. Others are named for what they remind us of, like the Mouse pulsar, which has a long, trailing tail of X-ray emission that looks like a tiny rodent scurrying through space. There's the Geminga pulsar, a name derived from Gemini gamma-ray source, but also meaning it's not there in the local dialect of Lombardy, Italy, a playful nod to how long it eluded detection. And who could forget the Lick pulsar, named after an undead being from folklore, simply because it's a millisecond pulsar that has essentially been reanimated by consuming material from a companion star. This mix of precise, clinical cataloging and creative, descriptive nicknames serves two vital purposes. For the scientific community, the formal coordinate-based names are absolutely essential. They prevent any confusion in research papers and databases, ensuring that when one team in Chile and another in Japan are discussing a specific neutron star, they are definitely talking about the exact same object. There are over 3,000 known pulsars, so this level of precision is non-negotiable. For the public, and even for astronomers in casual conversation, these nicknames make these incredible objects more memorable and relatable. They transform a distant, abstract point of data into a character with a story, helping to bridge the gap between complex science and human curiosity. It's a perfect partnership, the rigor of science paired with the poetry of the human imagination. Now, let's really try to wrap our minds around that density. It's one thing to hear the numbers, but it's another to truly picture it. Imagine if you could take something as colossal and majestic as Mount Everest with all its rock and mass and somehow compress it. Not into a small boulder or even a pebble. We're talking about crushing it down into a single, ordinary sugar cube that you could balance on your fingertip. That level of compression is what we're dealing with inside a neutron star. The entire object is essentially one gigantic atomic nucleus, but scaled up to the size of a city. This happens because the gravitational force during the supernova collapse is so overwhelmingly powerful that it completely overcomes every other force that usually keeps atoms apart. In a normal object like your hand or a planet, atoms are mostly empty space. The nucleus of an atom is like a single marble sitting in the middle of a sports stadium, and the electrons whizzing around the outer seats represent the atom's boundary. There's a tremendous amount of nothingness between one atom and the next, but inside a neutron star, that empty space is utterly eliminated. The incomprehensible pressure literally smashes those atomic stadiums together until the protons and electrons themselves are forced to merge, transforming into neutrons. These neutrons are then packed shoulder to shoulder, touching each other in a way that matter simply never does under normal conditions. It's the most efficient packing of matter possible in our universe. This extreme environment creates states of matter that physicists can only dream of replicating in labs on Earth. As we move from the crust inward, the conditions become even more bizarre. The outer crust is a solid, but it's made of a lattice of atomic nuclei, mostly iron, swimming in a sea of electrons. But this isn't any solid we know. It's 100 billion times stronger than steel. Go a little deeper, and the pressure becomes so immense that even those atomic nuclei can't hold their structure. They get squeezed together so tightly that they merge into bizarre, elongated shapes, tubes and sheets that physicists call nuclear pasta. This strange material is thought to be the strongest substance in the entire universe, and it's only possible under the insane pressure of a neutron star's interior. Deeper still, we reach the inner core, and here we venture into the true unknown. The pressure is so extreme that we're not entirely sure what happens to the matter. Some theories suggest the neutrons themselves might break down into a soupy sea of their own constituent particles, quarks, creating what's known as quark-gluon plasma, a state of matter that hasn't existed freely since the first moments after the Big Bang. Other theories propose that the core might become a superfluid, a frictionless state where the matter flows with absolutely no viscosity. It's a place where the fundamental rules of physics are written in extreme conditions we can only theorize about, making every distant neutron star a natural laboratory revealing the secrets of the universe's most basic building blocks. Now, to truly appreciate the bizarre physics of a neutron star, we have to look at the two numbers that define its very existence, its mass and its size. These figures are so extreme they almost sound like a contradiction. Imagine an object that contains more mass than our Sun, a star so huge that over 1.3 million Earths could fit inside it. Now take all that immense mass and crush it down, not into a sphere the size of a planet or even a moon. Crush it until it's only about 12 miles or 20 kilometers across. That's the staggering reality of a neutron star. To put that on a human scale, if you could drive a car around its equator at highway speed, you'd complete the entire journey in less than an hour. Every single bit of mass that was once a giant star is now packed into a space no larger than a major metropolitan city. This creates a density so profound that it warps the very fabric of space-time around it. But here's where it gets even more interesting. Despite all neutron stars being roughly the same petite size, their masses can vary. They typically fall between 1.1 and 2.3 times the mass of our Sun. Think about that for a second. You could have two neutron stars sitting side by side. One could contain twice the mass of the other, and yet they would both be the exact same physical size. It's a concept that defies all our earthly intuition. On Earth, if you have more of something, it takes up more space. But with matter this unimaginably dense, adding more mass doesn't make the star expand. The incredible gravity just packs it in even tighter, making the core more dense but not necessarily any larger. This is the ultimate example of nature finding a limit to how small it can make something for a given amount of stuff. But why is there a range, and what stops a neutron star from just getting more and more massive? This is where we encounter one of the most critical concepts in all of astrophysics, the Tolman-Oppenheimer-Volkoff limit, often called the TOV limit. Named after the physicists who calculated it, this isn't just another number, it's the ultimate line in the cosmic sand. The TOV limit is the maximum possible mass a stable neutron star can have before it loses its long, epic battle against gravity. It's the absolute upper boundary, thought to be around 2.3 solar masses. Up to this point, the neutrons themselves, packed together and supported by a quantum mechanical force called neutron degeneracy pressure, are able to push back against the star's own weight, preventing a total collapse. However, cross that line and the star's fate is sealed. If a neutron star gains just a little bit more mass, perhaps by pulling material from a companion star, and exceeds the TOV limit, the resistance of the neutron suddenly fails. The degeneracy pressure that was heroically holding up the star is instantly overwhelmed by the force of gravity. There is no force left in the known universe that can stop what happens next. In a fraction of a second, the entire structure catastrophically implodes. The star doesn't just get a little bit smaller, it collapses all the way down, vanishing from the observable universe and becoming a black hole. This makes every single neutron star a cosmic tightrope walker, perpetually balanced on the very edge of oblivion. They are the ultimate reminder that in our universe, even the most stable and powerful objects are governed by fundamental limits, and crossing them leads to the most dramatic transformations imaginable. This unimaginable density leads to one of the most direct and visceral consequences, an almost incomprehensible surface gravity. If you could somehow stand on the crust of a neutron star, which of course is impossible, the force pulling you down would be approximately 100 billion times stronger than the gravity we experience here on Earth. To put that in perspective, a person who weighs 150 pounds on our planet would suddenly weigh the equivalent of 15 billion tons. Every single cell in your body would be instantly and utterly flattened into a layer just 1 atom thick. It's a level of force that doesn't just bend the rules, it completely shatters any notion of a familiar physical environment. This extreme gravity also dictates the rules for leaving this cosmic prison. Here on Earth, we're used to the idea of escape velocity, the speed a rocket needs to achieve to break free of our planet's gravitational pull and journey into space. That number is about 7 miles per second, which is certainly fast, but it's achievable with our current technology. On a neutron star, the story is entirely different. To escape its gravitational clutches, any object would need to be launched at a velocity of roughly half the speed of light. That's over 93,000 miles per second. Not even light itself can escape unimpeded. While photons can get away, they lose a significant amount of energy fighting the gravitational pull, a phenomenon known as gravitational redshift that astronomers actually use to measure these stars' immense fields. This has profound implications for anything that gets too close to a neutron star, especially if it has a companion star in a binary system. The neutron star's gravity will relentlessly pull material, gas, and dust from its neighbor. But this matter isn't simply pulled down in a steady stream. Accelerated to those incredible velocities, the material doesn't just fall. It's slammed onto the surface with the energy of a continuous nuclear explosion. The infalling atoms are torn apart, creating a blazing hot shockwave that emits a torrent of X-rays, allowing us to detect these incredible events across interstellar space. It's a dramatic and violent process of cosmic accretion, where the neutron star grows in mass, one catastrophic impact at a time, perpetually dancing on the edge of becoming a black hole. For astronomers, this intense gravity presents a unique and frustrating challenge. It completely warps our view of the surface. The gravitational field is so powerful that it acts like a giant lens, bending the path of light emitted from the star's far side and bringing it into view. This means that, theoretically, more than 50% of the neutron star's surface could be visible to us at any one time, a phenomenon that completely defies our normal experience of only being able to see the hemisphere facing us. While this sounds like a benefit, it actually makes it incredibly difficult to create a precise map of the surface's features, like the location of its hotspots or the geometry of its magnetic fields. The light is so distorted that untangling the true image from the gravitationally lensed one becomes a monumental task in astrophysical modeling, turning every observation into a complex puzzle of light and gravity. If you thought the density and gravity of neutron stars were extreme, just wait until you hear about the sheer, raw heat they contain. Coming straight out of a supernova explosion, a newborn neutron star is one of the hottest objects in the entire universe. We're talking about an initial temperature that soars to over 1 million degrees Kelvin. To put that into some kind of perspective, the surface of our Sun, which feels impossibly hot to us, is a relatively cool 5,800 degrees. A brand new neutron star is more than 170 times hotter than that at its birth. This is thermal energy on a scale that's almost impossible to comprehend, born from the most violent and energetic event since the Big Bang itself. But unlike a campfire that simply radiates its heat into the air, a neutron star is cloaked in an incredible vacuum with no surrounding atmosphere to warm. This means its only way to cool down is by emitting radiation across the electromagnetic spectrum, and it does this with breathtaking intensity, shining most brightly in high-energy X-rays. For the first million years or so of its life, this surface emission is the primary way it loses its ferocious heat, gradually fading from a brilliant beacon of X-rays to a dimmer glow as the eons pass. However, the real magic, the truly efficient cooling mechanism, is happening deep within its core. This is where the process becomes utterly fascinating and relies on one of the most ghostly particles known to science, the neutrino. These tiny, nearly massless particles barely interact with normal matter. Trillions of them are passing through your body every second without you ever noticing. But inside a neutron star's core, where matter is crushed into exotic states, neutrinos are produced in absolutely staggering numbers. The extreme heat and density allow for processes called Urca processes, where neutrons and other particles interact, effectively converting thermal energy directly into neutrinos. These neutrinos then simply fly straight out of the star at nearly the speed of light, carrying away enormous amounts of energy with them without being slowed down at all. This neutrino cooling is phenomenally effective, acting like a cosmic air conditioning system that operates at a profound depth. For the first 1,000 years, this is the dominant way a neutron star sheds its heat, causing its internal temperature to plummet rapidly. After this initial burst of cooling, the pace slows, and the surface radiation takes back over as the primary method for the next several 100,000 years. By studying the specific temperature of a neutron star and understanding which cooling phase it's in, astronomers can actually make a very good estimate of its age. A hotter neutron star is likely a younger one, while a cooler one has been around for a much longer time, quietly radiating its remaining heat into the frozen depths of space. This turns each one into a cosmic clock, its temperature a direct readout of its long and violent history. While their density and heat are staggering, neutron stars also possess another defining feature that truly sets them apart: their unimaginably powerful magnetic fields. To even begin to grasp their strength, let's first consider the magnetic field of our own planet. Earth's magnetic field is what guides a compass needle. It's strong enough to protect us from solar winds, but it's also relatively gentle. A neutron star's magnetic field is a completely different beast. It is typically 1 trillion times stronger than Earth's. If you could bring a neutron star to within 100,000 miles of our planet, a distance that sounds vast but is less than half the distance to the Moon, its magnetic field would be so overwhelmingly powerful that it would wipe the information from every single credit card and hard drive on Earth. It is a force that doesn't just interact with matter, it completely dominates and controls it. The origin of this incredible magnetic power is a direct and dramatic consequence of the star's collapse. Think back to the progenitor star, the massive sun that existed before the supernova. Like our sun, it had its own magnetic field. A fundamental law of physics, the conservation of magnetic flux, tells us that if you take a magnetic field and compress the object it's tied to, the strength of that field increases dramatically. It's like an ice skater pulling their arms in to spin faster. As the star's core collapses from a sphere hundreds of thousands of miles wide down to a city-sized object, its magnetic field gets squeezed and concentrated along with it. The field lines, which were once spread out over a vast volume, are now crammed into an incredibly small space, amplifying their strength by a factor of 1 billion. This process creates the immensely powerful magnetic engines we observe. But not all neutron stars are created equal in this magnetic arena. We broadly classify them into 2 breathtakingly powerful categories. The first are the ordinary radio pulsars, which, as we've discussed, have those trillion times stronger than Earth's fields. Then there are the true monsters of the magnetic universe, the magnetars. These are the rare, extreme outliers, thought to make up only about 10% of neutron stars. A magnetar's magnetic field is another 1,000 times stronger than a typical pulsar's, making it a quadrillion times stronger than Earth. The magnetic field of a magnetar is so intense that it actually bends the very shape of atoms, stretching them into long, thin, pencil-like rods. It's a level of power that fundamentally alters the vacuum of space around it, creating a zone where quantum electrodynamic effects, usually only theoretical, become a tangible reality. This unimaginable magnetic force directly dictates how these objects behave and the kind of radiation they emit. For a standard pulsar, the magnetic field channels the star's rotational energy, funneling particles into beams that shoot out from the magnetic poles, creating the lighthouse effect we detect as regular pulses. But for a magnetar, the magnetic field is the primary source of its energy and its fury. The field is so unbelievably strong that it's under immense strain. It's like a colossal spring wound tighter than anything imaginable. Occasionally, this tension becomes too much to bear, and the crust of the neutron star, a material stronger than steel, can suddenly crack in what's called a starquake. This event releases a catastrophic amount of energy in a fraction of a second. When a magnetar experiences a starquake, it doesn't just create a little tremor. It unleashes a blast of gamma rays and X-rays so powerful that it can temporarily outshine every other star in our entire Milky Way galaxy combined, even from tens of thousands of light years away. These events, known as soft gamma repeaters or giant flares, are among the most violent and energetic outbursts in the modern universe. For a few terrifying seconds, a single city-sized object can release more energy than our sun will emit over 100,000 years. It's a spectacular and terrifying demonstration of how the magnetic fields of neutron stars aren't just a curious feature. They are the engine of some of the most extreme and luminous phenomena we have ever witnessed in the cosmos. This incredible precision in their rotation brings us to one of the most useful applications of pulsars, their role as the universe's most accurate natural clocks. Because their spin is so stable and predictable, the timing of their pulses can be measured with astonishing accuracy. The best pulsars rival, and in some cases even surpass, the precision of atomic clocks here on Earth. Their pulses can be timed to within 100 nanoseconds or better, meaning we can predict when each pulse will arrive across interstellar distances with an error of less than 1/10,000,000th of a second. This isn't just a neat scientific trick, it's a tool that allows us to conduct incredible experiments. Scientists use these cosmic clocks to test Einstein's theory of general relativity in ways that would be impossible in any Earth-based laboratory. For instance, when a pulsar is in a binary system with another neutron star, the extreme gravity of the two orbiting objects creates tiny, measurable wrinkles in spacetime. By meticulously tracking the arrival times of the pulses as the pulsar moves through these warps, astronomers can see if the pulses are delayed by exactly the amount Einstein's equations predict. In every case so far, the pulsars have confirmed relativity with breathtaking precision, making them our best allies in probing the fundamental nature of gravity itself. Their reliability also opens up a truly futuristic possibility: pulsar-based navigation for interstellar travel. Much like ancient sailors used lighthouses to navigate the seas, a spacecraft could use the predictable pulses from a network of known pulsars to triangulate its position anywhere in the galaxy. Each pulsar has a unique signature, its rotation period and direction, effectively giving it a cosmic GPS coordinate. By comparing the expected arrival times of pulses from at least 3 different pulsars with the times actually measured on board a ship, a computer could calculate its precise location in 3-dimensional space. This concept, often called pulsar timing navigation, isn't just science fiction. NASA has already tested this technology with the Sextant experiment on the International Space Station, successfully using X-ray pulses from pulsars to determine the station's position in orbit. Of all these cosmic lighthouses, few are as famous or as historically important as the Crab pulsar. Nestled at the very heart of the Crab Nebula, the beautiful remnant of a supernova that was observed to explode by Chinese astronomers in the year 1054, this pulsar is a mere 33 milliseconds old, spinning 30 times every single second. It's a relatively young and energetic object, and it's one of the very few pulsars that can be seen flashing visibly with a large amateur telescope. Its discovery in 1968 provided the crucial smoking gun evidence that directly linked pulsars to neutron stars and connected them to supernova remnants, closing a key loop in our understanding of stellar life cycles. It serves as a constant reminder that these distant pulsing beacons are not just abstract curiosities. They are the dynamic, powerful engines left behind after some of the universe's most spectacular explosions. So how do we actually detect these cosmic lighthouses from thousands of light years away? The secret lies in a special kind of telescope designed not to see light but to listen to the universe. Radio telescopes are the workhorses of pulsar astronomy. These aren't your typical backyard telescopes with lenses and mirrors. They're often massive parabolic dishes, some as large as a football field, designed to collect the faint whispers of radio waves traveling across the cosmos. A pulsar's beam, while containing various types of radiation, is often brightest and most easily detectable in the radio part of the electromagnetic spectrum. As the neutron star spins and its beam sweeps across our line of sight, the radio telescope picks up that brief, incredibly regular burst of energy, a pulse that might only last a few milliseconds, and then it's gone until the next rotation. But finding these needles in the cosmic haystack is a monumental task. The signals are incredibly faint after their long journey, often buried under a mountain of background static from other celestial objects and even human-made radio interference. To overcome this, astronomers don't just take a single snapshot. They engage in a process called time series analysis. They point a radio telescope at a patch of sky and collect data over hours, sometimes even days. A supercomputer then analyzes this long recording, applying a mathematical algorithm called a fast Fourier transform. This process is essentially a cosmic search for rhythm, sifting through the noise to find any perfectly repeating signal, no matter how faint. It's like trying to pick out the steady beat of a single drum from the roar of a massive stadium crowd. This painstaking work has been pioneered by some of the world's great observatories. The Parkes Observatory in Australia, affectionately known as the Dish, has been one of the most prolific pulsar hunters in history. Its 64-meter antenna, sitting in a remote valley to avoid radio interference, has discovered over half of the more than 3,000 known pulsars. Its success is partly due to its southern hemisphere location, giving it a unique view of our galactic center and the Magellanic Clouds. Meanwhile, the Arecibo Observatory in Puerto Rico, before its unfortunate collapse, used its immense 305-meter dish to find some of the most exotic pulsars, including the first binary system and the first millisecond pulsars. These facilities have provided the raw data that has fundamentally shaped our understanding of these objects. The hunt, however, is far from over. Today, the search is being supercharged by a new generation of telescopes and international collaborations. Projects like the Low-Frequency Array in Europe and the Murchison Widefield Array in Australia use a different technique called interferometry, which links dozens or even hundreds of small antennas together to act as one giant telescope, scanning vast areas of the sky at once. But the future is already here with the 500-meter aperture spherical radio telescope in China. FAST is the largest single-dish radio telescope on the planet, nestled in a natural karst depression to protect it from interference. Its sheer size gives it unprecedented sensitivity, allowing it to detect pulsars that are too faint or too fast spinning for previous telescopes to find. It's already discovering hundreds of new candidates, pushing the boundaries of what we thought was possible and reminding us that for every pulsar we've found, there are countless more waiting to be discovered, each one holding a new clue to the extremes of our universe. While the steady, rhythmic ticking of most pulsars is impressive, some neutron stars take rotational speed to a level that utterly defies belief. We call these the millisecond pulsars, and they are the true Formula One race cars of the cosmos. Imagine an object with more mass than our Sun, a sphere over 12 miles wide, completing a full 300, and 60-degree rotation not every few seconds but hundreds of times every single second. The fastest known, Pulsar J1748-2446 AD, spins an astonishing 716 times per second. At that rate, its equator is moving at a significant fraction of the speed of light. The centrifugal forces involved are so immense that if it were spinning just a little bit faster, it would literally tear itself apart. These speed demons aren't born spinning this rapidly. They are old neutron stars that have been given a spectacular second lease on life through a violent and intimate cosmic partnership. They exist in binary systems with a companion star. Over millions of years, the neutron star's immense gravity pulls a stream of gas from its neighbor. This material doesn't just fall onto the surface, it spirals down, forming a vast, hot disk of accreting matter around the pulsar. As this gas crashes onto the surface, it doesn't just add mass, it transfers an enormous amount of angular momentum, the same principle that makes an ice skater spin faster when they pull their arms in. This process acts like a continuous cosmic throttle, relentlessly spinning the neutron star up to these incredible velocities. The older pulsar is effectively recycled into a youthful, hyper-spinning marvel. This accretion process does more than just make them fast, it makes them incredibly stable. All that infalling mass essentially tops up their energy reserves, making their rotation periods astonishingly precise and reliable. This phenomenal stability is what makes millisecond pulsars some of the most valuable tools in the astrophysicist's toolkit. They become the regular ticks of a galactic scale clock, and it's this property that allows for one of the most exciting experiments in modern astronomy, the hunt for gravitational waves using pulsar timing arrays. Here's how it works on a breathtaking scale. Astronomers carefully monitor the precise arrival times of pulses from an entire array of these millisecond pulsars scattered across our galaxy. They are looking for incredibly subtle, correlated shifts in the timing. The hypothesis is that as long-wavelength gravitational waves, ripples in the fabric of spacetime caused by the collisions of supermassive black holes wash over our galaxy, they will minutely stretch and compress the space between Earth and each pulsar. This would cause the pulses to arrive just a few tens of nanoseconds early or late in a specific, synchronized pattern across the entire array. It's like trying to detect a single wrong note in a symphony orchestra playing in perfect harmony for a decade, but the implications are profound. This method allows us to sense the low-frequency hum of the universe, a gravitational wave background that other detectors like LIGO cannot hear, opening a completely new window into the most massive and violent events in the cosmos. While the image of a lone neutron star spinning silently in the void is a powerful one, the universe often prefers dramatic partnerships. A surprising number of these ultra-dense objects are not alone. They are locked in a gravitational dance with another star, creating a binary system that becomes a stage for some of the most energetic and informative phenomena in the cosmos. These pairings are far from peaceful. They are intense, often violent relationships where gravity dictates a complex and spectacular interplay of matter and energy. One of the most spectacular results of this partnership is known as an X-ray binary. This occurs when the neutron star's companion is a more typical star, like a red giant or a main sequence star similar to our Sun. The neutron star's immense gravity acts like a cosmic vacuum, relentlessly pulling a stream of gas from its stellar partner, but this material doesn't fall directly onto the surface. Instead, it forms a swirling, incredibly hot disk of plasma called an accretion disk, spiraling inward at nearly the speed of light. The friction within this disk heats the material to temperatures of millions of degrees, causing it to emit a tremendous flood of high-energy X-rays long before it even reaches the surface. It is this brilliant, blazing disk that makes X-ray binaries shine so brightly in that part of the spectrum, acting as a beacon that allows us to spot these systems from across the galaxy. The consequences of this mass transfer can be truly explosive. In some systems, the infalling gas doesn't land smoothly. Instead, it can build up on the neutron star's surface until it triggers a runaway thermonuclear explosion. In a flash, the accumulated hydrogen or helium ignites all at once, unleashing a colossal burst of X-rays and gamma rays that can outshine entire galaxies for a few brief, spectacular seconds. Astronomers call these events X-ray bursts, and they are a direct window into the extreme nuclear physics happening on the surface of these stars. We can actually observe the aftermath of these eruptions as the burning layer cools, giving us critical data about the composition and temperature of the neutron star's outer layers. But the drama doesn't end there. When the binary partner is another neutron star or even a black hole, the stakes become infinitely higher. Two neutron stars orbiting each other represent one of the most extreme environments imaginable. Their dance is not a stable one. Einstein's theory of general relativity predicts that such a close, massive binary system will lose energy by emitting gravitational waves, ripples in the fabric of spacetime itself. This loss of energy causes the two stars to slowly spiral inward, their orbits decaying over millions of years in a fateful procession toward an inevitable collision. The final act of this cosmic ballet is a kilonova, one of the most catastrophic and productive events in the universe. When the two neutron stars finally merge, they do not go quietly. The collision unleashes a titanic explosion, briefly shining with the light of a billion suns and scattering a vast cloud of hot, neutron-rich debris. Within this expanding cloud, conditions are so extreme that it becomes a cosmic forge, creating vast quantities of the universe's heaviest elements through a process called rapid neutron capture. It is in these magnificent, violent events that most of the gold, platinum, and other precious metals in the universe are born, later to be incorporated into new stars, planets, and even life itself. The 2017 observation of such a merger, known as GW 170817, was a landmark moment confirming that these events are the primary source for many of the heavy elements we find on Earth and throughout the cosmos. Studying these binary systems provides far more than just a spectacle. It gives us a powerful tool for fundamental science. The precise timing of a pulsar's ticks in a binary system allows astronomers to map the star's orbits with incredible accuracy. Tiny deviations in the pulse arrival times can reveal the presence of planets orbiting the system, measure the masses of the stars with unparalleled precision, and provide the most stringent tests yet of general relativity under conditions of extreme gravity. Each binary system is a natural laboratory, offering a unique experiment that we could never hope to recreate on Earth, helping us to unravel the deepest laws governing the universe. Now, let's turn our attention to one of the most spectacular events in the cosmos, where the serene dance of a binary system erupts into a cataclysm of creation. When two neutron stars are locked in a close orbit, their fate is sealed by the relentless pull of gravity and the subtle whisper of spacetime itself. As they whirl around each other, this incredible motion generates ripples in the fabric of the universe, gravitational waves. These aren't waves of light or sound, they are literal distortions in the dimensions of space and time, predicted by Einstein a century ago. The emission of these waves slowly but surely drains energy from the system, causing the two stars to spiral inward closer and closer over millions of years. Their final moments together are a crescendo of motion, accelerating to a significant fraction of the speed of light just before they collide. This collision is not a simple crash. It is a kilonova, an explosion of such staggering energy and brilliance that it briefly outshines an entire galaxy. And on August 17, 2017, for the very first time, humanity was watching. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, along with its European counterpart Virgo, detected the distinct chirp of gravitational waves from an event designated GW 170817. This was the sound of two neutron stars, each about 1.4 times the mass of our Sun, meeting their end about 130 million light-years away. But the real revolution began just seconds later. NASA Fermi Gamma-Ray Space Telescope detected a short gamma-ray burst coming from the same patch of sky. For the first time, we had both gravitational waves and light from the same cosmic event. This triggered the largest astronomical observation campaign in history, with telescopes across the globe and in space swiveling to witness the aftermath. What they saw was the breathtaking glow of a kilonova, and within that expanding cloud of hot debris, the universe was performing its most spectacular alchemy. The extreme conditions in the aftermath of the merger, an environment flooded with neutrons, are perfect for a process called rapid neutron capture, or the R process. Atomic nuclei are bombarded by a dense torrent of free neutrons, allowing them to grab these particles and build themselves up into heavier and heavier elements in a matter of seconds. It is in these magnificent, violent events that the universe forges most of its gold, platinum, silver, and other precious elements like uranium and thorium. The GW-170817 event alone is estimated to have produced an amount of gold with a mass many times that of our entire planet. So, the gold in your jewelry or the platinum in a catalytic converter was almost certainly born in the fiery aftermath of a neutron star collision that occurred billions of years ago, before our own solar system even formed. This historic observation marked the dawn of multi-messenger astronomy, a powerful new way of understanding the universe. Instead of relying solely on light, whether it's visible, X-ray, or radio, we can now combine that information with the message carried by gravitational waves and even neutrinos. It's like previously only being able to watch a silent movie about the cosmos, and now suddenly having the soundtrack as well. By correlating these different signals, scientists were able to confirm long-held theories about the origin of heavy elements and the nature of gamma-ray bursts. They could pinpoint the location of the event in a distant galaxy, measure the expansion rate of the universe in a new way, and study the properties of matter under the most extreme densities imaginable. A single event provided answers to questions that had puzzled physicists and astronomers for decades, all because we learned to listen to the ripples in space-time and immediately turned our eyes to the sky. Now, the sheer violence of that merger creates an environment unlike any other, a cosmic pressure cooker where the universe forges its heaviest elements. This is where the R process, or rapid neutron capture process, takes center stage. To understand it, picture an atomic nucleus trying to grow. Normally, positively charged protons repel each other, making it hard to build heavy elements through simple fusion. But in the neutron-rich debris of a kilonova, nuclei are bombarded by an incredible flood of free neutrons. These neutrons, having no electrical charge, slam into the nuclei without any repulsion. A nucleus can rapidly capture a dozen or more of these neutrons in just a fraction of a second, building itself into an extremely heavy, unstable form. This unstable nucleus then undergoes radioactive decay, transforming some of those neutrons into protons, which effectively creates a brand new, heavier element. This cycle of rapid neutron capture and subsequent decay happens in a blink of an eye, allowing elements far heavier than iron to be synthesized almost instantaneously. It's this very process that is responsible for creating roughly half of all the elements heavier than iron in the entire universe. The gold in a wedding ring, the platinum in a medical device, the uranium that can power a city, these aren't forged in the peaceful hearts of living stars. They are born in the most violent and spectacular explosions imaginable, the collisions of neutron stars. A single kilonova event can manufacture hundreds of times the mass of the Earth in these precious heavy elements, scattering them out into the galactic environment where they eventually become part of new generations of stars, planets, and even life itself. We are literally made of stardust, but our most precious metals are made of neutron star dust, the remnants of ancient cosmic cataclysms. For scientists, observing a kilonova is like finding the missing piece of a century-old puzzle. For decades, we knew these heavy elements existed, but their origin was one of astrophysics' greatest mysteries. We knew they couldn't be made in ordinary supernova or in the cores of stars in sufficient quantities. The theoretical work pointed to the R process, but the extreme conditions required, an intense neutron flux, were thought to be incredibly rare. The confirmation that kilonovae are the primary source of these elements was a monumental breakthrough. By analyzing the light from a kilonova, astronomers can directly see the signature of these heavy elements being created in real time. The light curve and spectrum of the explosion change over days and weeks as different radioactive elements decay, painting a vivid picture of the nucleosynthesis happening within the expanding cloud. This makes kilonovae far more than just a beautiful cosmic fireworks display. They are essential laboratories for understanding the chemical evolution of our galaxy and the universe itself. Every time we detect one, we are witnessing the enrichment of the cosmos, the mechanism that fills space with the raw materials for rocky planets and, potentially, life. It connects the immense scale of colliding stars to the very personal scale of the world around us, revealing that the history of a gold necklace is written in the violent death of two of the universe's most extreme objects. Venturing beyond our own galactic neighborhood, we now turn our gaze to the most remote neutron stars ever detected, objects so distant that their faint whispers of light have traveled for hundreds of millions of years just to reach our telescopes. One of the most stunning examples is a magnetar located in the galaxy NGC 253, also known as the Sculptor Galaxy. This star system is approximately 11.4 million light-years away, which means the brilliant flash of X-rays we detected from its surface actually began its journey to Earth at a time when our human ancestors were just beginning to walk upright. To spot a single, city-sized object at such an incredible intergalactic distance is a testament to both the raw power of these cosmic engines and the remarkable sensitivity of our modern observatories. The primary obstacle to finding these far-flung objects is quite simply their immense distance and resulting faintness. Even the most energetic pulsar is an incredibly tiny speck of light when viewed from another galaxy. Its regular radio pulses, which might be strong and clear from within the Milky Way, become almost impossibly weak, drowned out by the background radio chatter of the universe and the sheer noise of our own atmosphere. Detecting them requires not just powerful telescopes, but also immense amounts of observation time and sophisticated data processing to dig that faint, rhythmic signal out of the overwhelming static. This is where astronomers have had to get creative, often relying on their high-energy emissions rather than their radio pulses to make a positive identification. Neutron stars, especially magnetars and those in X-ray binary systems, can unleash tremendous bursts of X-rays and gamma rays. These sudden, brilliant flashes can be detected by space-based telescopes like NASA Chandra X-ray Observatory and the Neil Gehrels Swift Observatory, even from staggering cosmological distances. A single, powerful magnetar flare can momentarily outshine its entire host galaxy in X-rays, creating a beacon that cuts across the universe and pinpoints its location for us. By focusing on these dramatic, high-energy outbursts, scientists can identify candidate neutron stars in other galaxies and then conduct follow-up observations to confirm their nature. Another powerful, though more rare, technique is gravitational lensing. This is a dramatic validation of Einstein's theory of general relativity, where the gravity of a massive object like a galaxy or a cluster of galaxies acts as a natural cosmic lens. It bends and magnifies the light from objects lying far behind it. If a distant neutron star happens to be in the precise alignment behind such a lens, its light can be amplified, sometimes by a factor of 10 or more, making it temporarily bright enough for us to study in detail. This natural telescope allows us to see details we otherwise never could, and it has been used to study objects in the very early universe. While finding a lensed neutron star is like winning the cosmic lottery, it provides an unparalleled opportunity to probe the properties of these objects at distances that were once thought to be completely unreachable. Studying these most distant neutron stars is about far more than just breaking records. It provides us with a critical new perspective on the universe. Each one is a fossil relic from a different galactic environment, telling us about the star formation history and the metal content of its host galaxy. By comparing them to neutron stars in our own Milky Way, we can understand how their properties might change in different cosmic settings. Furthermore, their incredible distance makes them perfect tools for cosmology. Their pulsars can be used to measure the amount of tenuous material floating in the vast intergalactic space between galaxies, and their light can help us map the large-scale structure of the universe itself. Each faint pulse from the darkness is a message in a bottle, carrying with it secrets from a faraway island universe and helping us piece together the grand story of the cosmos. Measuring the vast distances to these cosmic lighthouses is a fascinating puzzle in itself, one that requires astronomers to use every trick in their toolkit. For the relatively closer neutron stars within our own galaxy, a method called parallax is often the first and most reliable approach. You can demonstrate this yourself by holding a finger up in front of your face and closing one eye, then the other. Your finger appears to shift position against the background. Astronomers use the same principle, but on a galactic scale. They observe a neutron star from opposite sides of Earth's orbit around the Sun, a baseline of about 2 astronomical units or 186 million miles. By precisely measuring the tiny apparent shift in the star's position against more distant background objects, they can use simple trigonometry to calculate its distance with remarkable accuracy. This method works beautifully for objects within a few thousand light-years of Earth, providing a solid foundation for our cosmic distance ladder. But what about the pulsars that are much farther away, across the vast expanse of the Milky Way or even beyond? For these distant objects, astronomers rely on a clever technique that uses the pulsar's own signal against the environment of space itself. As a pulsar's radio waves travel through the interstellar medium, the thin soup of gas and plasma that exists between the stars, they interact with free electrons. These electrons act like a subtle cosmic prism, causing lower-frequency radio waves to travel slightly slower than higher-frequency ones. This effect is called dispersion. The result is that the higher-frequency pulses from a single rotation arrive at our telescopes a fraction of a second before the lower-frequency ones. By measuring this time delay across different frequencies, astronomers can calculate a value known as the dispersion measure. This dispersion measure is essentially a count of how many free electrons the signal has passed through on its journey to Earth. The next step is to estimate the average density of these electrons along that line of sight. By using models of the Milky Way's electron distribution, they can then estimate the total distance the signal has traveled. It's not as precise as parallax and relies on our sometimes imperfect models of the galaxy's structure, but it provides a crucial distance estimate for thousands of pulsars that would otherwise be impossible to gauge. Another powerful method involves linking a neutron star to its birthplace. Many neutron stars are found zooming through space at incredible speeds, having received a kick from the asymmetric supernova explosion that created them. By tracing their path backwards through space and seeing if it intersects with a known supernova remnant, astronomers can often pinpoint their origin and thus their distance, since the distance to the remnant cloud of gas is often easier to measure. This is like finding a runaway cannonball and figuring out which cannon it was fired from by looking at its trajectory. The famous Crab Pulsar, for instance, is definitively linked to the Crab Nebula, the remnant of a supernova observed in 1054, which gives us a very confident distance measurement. For the most distant neutron stars in other galaxies, the challenge is even greater. Here, astronomers often use the overall properties of the host galaxy itself to get a distance estimate. By measuring the redshift of the galaxy's light, how much its light is stretched to longer wavelengths by the expansion of the universe, they can determine how far away the entire galaxy is. Any neutron star within that galaxy is then assumed to be at roughly the same distance. While this doesn't give a precise measurement for the individual star, it places it in the right cosmological neighborhood. The quest for greater precision is never-ending, and new technologies are continually refining our measurements. Very Long Baseline Interferometry, or VLBI, networks multiple radio telescopes across continents to create a virtual telescope the size of the Earth itself. This dramatically increases resolution, allowing for incredibly precise positional measurements and even better parallax calculations. These ongoing efforts are vital because an accurate distance is the key that unlocks so many other secrets. It allows scientists to convert the observed brightness of a neutron star into its true luminosity, to understand its velocity through space, and to model its evolution with far greater confidence. Every decimal point of accuracy in a distance measurement brings us one step closer to fully understanding the life and power of these incredible cosmic objects. And this incredible connection between a newborn neutron star and its supernova remnant offers one of the most powerful tools an astronomer has, a cosmic birth certificate. By studying the supernova remnant, scientists can accurately date the neutron star at its heart. The process is like watching a crime scene investigation unfold on a galactic scale. When a massive star explodes, it blasts its outer layers outward at thousands of kilometers per second. This expanding shell of gas, the supernova remnant, glows brightly as it rams into the surrounding interstellar medium, sweeping up material and creating a beautiful, intricate nebula. By measuring the current size of this expanding nebula and knowing its approximate velocity, astronomers can simply calculate backwards to determine when the explosion must have occurred. This gives us a very precise age for the neutron star within, a timeline that is often corroborated by historical records. The most famous example is, of course, the Crab Nebula. Chinese and Arab astronomers in the year 1054 documented a guest star so bright it was visible in the daytime for weeks. Tracing the expansion of the nebula we see today perfectly aligns with that date, telling us the Crab Pulsar is exactly 970 years old. These glowing remnants are far more than just a pretty picture. They are a rich fossil record of the explosion itself. The composition of the gas tells a detailed story about the progenitor star. By analyzing the light emitted by the nebula with spectrometers, scientists can identify the specific elements present. Finding large amounts of oxygen, neon, and magnesium suggests the original star was of a certain mass, while different ratios of elements point to a different starting point. This allows astronomers to classify the type of supernova and understand the internal processes of the star that existed just before its catastrophic demise. It's like sifting through the debris after a volcanic eruption to understand the geology that led to the blast. Furthermore, the shape and structure of the remnant provide crucial clues about the symmetry of the explosion. A perfectly spherical remnant suggests a relatively even detonation, while a wildly asymmetric, ragged nebula indicates a profoundly uneven collapse, which helps explain the powerful kicks that send neutron stars careening across the galaxy at incredible speeds. The remnant acts as a permanent imprint of the explosion's violence, freezing that moment in time for us to study millennia later. By combining the data from the neutron star, its spin, magnetic field, and velocity with the data from its surrounding remnant, we can reconstruct the entire story of its birth, from the final moments of the progenitor star to the initial conditions of the ultra-dense object it became. This powerful synergy turns a single celestial object into a complete case study, helping us refine our models of stellar life cycles and the violent deaths that create the most exotic objects in the universe. Their explosive births and dramatic lives mean neutron stars are far more than just isolated cosmic curiosities. They are active and influential players in the grand story of their galaxies. This role begins the moment they are born. A supernova explosion doesn't just create the neutron star, it violently expels the outer layers of the progenitor star, seeding the surrounding interstellar space with newly forged elements. This ejected material, rich with oxygen, carbon, silicon, and iron, expands outwards for thousands of light years, eventually mixing with the tenuous gas and dust between the stars. This process, repeated by countless supernovae over billions of years, is fundamental to the chemical enrichment of a galaxy, gradually increasing the metal content of the interstellar medium and providing the raw materials for new generations of stars, planets, and even life. But the influence of a neutron star doesn't end after its fiery birth. Throughout its long life, it continues to shape its environment through powerful feedback mechanisms. As it spins, a pulsar generates a fierce wind of highly energetic particles and radiation, all channeled by its immense magnetic field. This wind creates what's known as a pulsar wind nebula, a glowing cloud of energized particles that expands into the surrounding space. The most famous example is the Crab Nebula, which is powered entirely by the energetic output of the pulsar at its heart. These nebulae inject tremendous amounts of energy into their local environment, heating the interstellar gas and preventing it from cooling and collapsing to form new stars too quickly. In this way, neutron stars act as a form of galactic regulation, their powerful winds helping to control the pace and location of star formation within a galaxy. Perhaps their most profound contribution, however, comes from their incredible final acts in binary mergers. As we've seen, the collision of two neutron stars is the universe's primary forge for the heaviest elements like gold, platinum, and uranium. The kilonova explosion that results from such a merger does not simply create these elements. It violently blasts them out into the galactic environment at speeds approaching a significant fraction of the speed of light. This process scatters these precious metals far and wide, ensuring they are incorporated into vast clouds of gas that will one day coalesce into new solar systems. The rocky planets that form within these systems will therefore be seeded with these heavy elements. Every time we encounter a vein of gold or a deposit of uranium on Earth, we are witnessing the direct legacy of a neutron star merger that occurred billions of years before our own sun was born. This continuous cycle of creation and distribution makes neutron stars indispensable agents of galactic evolution. They take the simple hydrogen and helium from the Big Bang and, through their life cycles of fusion, explosion, and collision, progressively build more complex atoms. They then ensure those atoms are disseminated throughout the galaxy, enriching the cosmic ecosystem. Without these dramatic events, the universe would be a far simpler and less chemically interesting place, devoid of the elemental diversity necessary for planets like Earth and the life that calls it home. Their story is a powerful reminder that the largest-scale processes of a galaxy are intimately connected to the smallest-scale properties of matter, linking the fate of atoms to the destiny of the cosmos itself. Delving into the heart of a neutron star is perhaps the greatest theoretical challenge in all of modern physics. We've explored their mind-boggling density and immense gravity, but what is the actual nature of matter crushed into such an incomprehensible state? The truth is, we don't know for certain. The interior of a neutron star is a realm of such extreme pressure and density that it becomes a natural laboratory for states of matter that simply cannot exist anywhere else, not even in our most powerful particle colliders. Scientists use the term exotic matter to describe these theoretical substances, and they represent the final frontier of our understanding of the universe's fundamental rules. To even begin modeling these mysterious interiors, physicists rely on something called an equation of state. Think of this not as a single equation, but as a complete theoretical framework, a complex recipe that describes how matter behaves and responds to pressure at these insane densities. It's the ultimate mathematical link between a neutron star's mass and its radius. Different equations of state make different predictions. A softer equation of state might predict that adding more mass will cause the star to shrink significantly, while a stiffer one might suggest the size stays more constant. The problem is, we have numerous plausible equations of state, and we don't yet know which one correctly describes reality. By measuring the masses and sizes of real neutron stars, we can rule out some theories and support others, slowly zeroing in on the true nature of matter at its limit. So, what are the leading candidates for what lies beneath that solid billion times stronger than steel crust? As we journey inward, the first layer of exotic matter physicists propose is known as nuclear pasta. This isn't a whimsical name without meaning. It's a direct description of the shapes atomic nuclei might be forced into. Under pressures 100 trillion times greater than Earth's atmosphere, nuclei can no longer maintain their spherical forms. They get squeezed into elongated tubes, flat sheets, and even bubble-like structures that remarkably resemble types of pasta like spaghetti, lasagna, and gnocchi. This nuclear pasta is theorized to be the strongest material in the entire universe, forming a rigid and incredibly complex barrier deep within the star. Venturing further toward the core, the conditions become so severe that even individual neutrons might not survive intact. One compelling theory suggests that the neutrons themselves break down into their constituent parts, quarks. In our everyday world, quarks are forever locked inside protons and neutrons by a phenomenon called confinement. But inside a neutron star's core, the pressure might be so unimaginably high that it overwhelms this force, dissolving the boundaries between neutrons and creating a soup of free-floating up, down, and strange quarks. This state is known as quark matter or quark-gluon plasma, a primordial substance that hasn't existed freely since the first microseconds after the Big Bang. Finding evidence of a quark star would be a monumental discovery, confirming an entirely new phase of matter. Another fascinating possibility is the presence of hyperons. These are exotic particles similar to neutrons and protons, but containing at least one strange quark. At the extreme densities in the core, it might become energetically favorable for regular neutrons to convert into these heavier, stranger particles. The problem is, the presence of hyperons tends to soften the equation of state, making it harder for the star to support itself against gravity. If hyperons are abundant, it would lower the maximum possible mass a neutron star can have, which could conflict with our observations of very heavy neutron stars. This creates a fascinating puzzle known as the hyperon puzzle that theorists are still working to solve. Finally, there is the strong possibility that the inner core is a superfluid. A superfluid is a state of matter that flows with absolutely zero viscosity or friction. On Earth, we can create tiny superfluid samples of liquid helium at near absolute zero temperatures. Inside a neutron star, the neutrons themselves might form a superfluid, a swirling, frictionless ocean. This wouldn't make the star slippery. Instead, it helps explain several observable phenomena, like why older pulsars sometimes exhibit sudden tiny jumps in their spin rate called glitches. These glitches are thought to be caused by sudden transfers of angular momentum between the solid outer crust and the superfluid interior, like the liquid inside a spinning egg suddenly grabbing onto the shell. Ultimately, understanding the true interior composition of a neutron star is about so much more than just satisfying our curiosity. It directly tests the very laws of physics under conditions we can never hope to replicate on Earth. Each new observation, whether it's of a massive neutron star, a sudden glitch, or the gravitational waves from a merger, provides a crucial data point that helps us discriminate between these wild theories. The exotic matter hidden within these distant city-sized objects holds the key to unlocking secrets about the strongest forces in nature, the fundamental building blocks of everything we see, and the ultimate fate of matter itself. Now, let's turn to one of the most fascinating and cutting-edge ideas in modern astrophysics: the possibility that these distant, ultra-dense objects might be acting as nature's own dark matter detectors. For decades, scientists have been searching for this elusive substance, which makes up about 85% of all the matter in the universe but has never been directly observed. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. We only know it's there because of its gravitational pull on galaxies and galaxy clusters. But if we can't see it, how can we possibly hope to study it? This is where neutron stars enter the picture in a truly spectacular way. Because of their immense gravity and incredible density, neutron stars could be the perfect trap for dark matter particles. Think of a neutron star as a gigantic cosmic fishing net drifting through the galaxy. As it moves, it sweeps through the vast, invisible sea of dark matter that is thought to permeate every corner of space. According to some theories, dark matter particles, often called WIMP or weakly interacting massive particles, could be gravitationally captured by the neutron star. Their trajectories would be bent by the star's powerful gravity, causing them to lose energy and become stuck in orbit, eventually spiraling inward to be absorbed into the star itself. Over billions of years, a neutron star could accumulate a significant amount of dark matter in its core. This accumulation could have two potentially observable effects, offering us an indirect way to detect the undetectable. The first is on the star's temperature. As we discussed, neutron stars cool down over time primarily by emitting neutrinos from their cores. But if a quantity of dark matter is concentrated in the center, these particles could act as an additional cooling mechanism. Dark matter particles could interact with the regular matter, the neutrons, and carry away thermal energy even more efficiently than neutrinos do. This would cause an older neutron star to cool down much faster than our standard models predict. So, if astronomers were to find a very cold, ancient neutron star that seems to have lost its heat too quickly, it could be a telltale sign that dark matter is at work, acting as a sort of cosmic heat sink deep within its core. The second possibility is even more dramatic. Some theories suggest that if enough dark matter builds up in the core of a neutron star, the particles could eventually become so densely packed that they collapse under their own gravity, triggering a chain reaction that ignites the entire dark matter reservoir. This event would release a tremendous burst of energy, potentially appearing as a sudden, unexplained flash of gamma rays or a unique signature of neutrinos emanating from an otherwise quiet neutron star. Observing such an event would be a monumental breakthrough, providing not just evidence for dark matter, but crucial information about its properties and how it interacts with normal matter. This makes the most distant neutron stars, especially those that drift alone in the halos of galaxies where dark matter is thought to be most concentrated, incredibly valuable natural laboratories. By carefully monitoring the temperature and energy output of these isolated objects over long periods, astronomers are essentially conducting a galaxy-wide experiment. They are looking for any anomalies in their behavior that can't be explained by conventional physics. Each distant neutron star is a potential sentinel, silently recording its interactions with the dark universe. While this research is still in its early stages and highly theoretical, it demonstrates how these extreme objects are more than just relics of dead stars. They are active tools, helping us probe the deepest and most profound mysteries of the cosmos, mysteries that lie literally in the dark. While we often picture the universe as a silent, empty void, the truth is far more musical, especially when it comes to neutron stars. These cosmic powerhouses don't just create incredible visuals, they produce rhythms and vibrations that can be translated into sounds we can actually hear. Through a process called data sonification, scientists take the precise, regular pulses of a spinning neutron star and convert them into audio frequencies, allowing us to listen to the cosmic songs of these distant objects. For instance, the rapid metronomic ticking of the Crab pulsar, which spins 30 times a second, becomes a steady, mid-range hum when sped up into the range of human hearing. It's a haunting and beautiful reminder that these aren't just abstract points of light, they are dynamic objects with a tangible rhythm. This translation from data to sound isn't just a neat public outreach trick, it's a legitimate tool for scientific discovery. The human ear is remarkably good at detecting subtle patterns, rhythms, and changes in tone that might be easy to miss when simply looking at a graph or a sheet of numbers. By listening to the sounds of a pulsar, astronomers have sometimes been able to identify tiny irregularities, like a slight stutter or a double pulse, that could indicate a glitch in the star's rotation or a complex structure in its magnetic field. It adds an entirely new dimension to data analysis, allowing researchers to literally hear the universe speaking to them through these rhythmic beats. Some of the most fascinating sounds come from neutron stars that are experiencing true cosmic violence. The mergers of these incredibly dense objects create the most powerful gravitational waves in the universe, and these ripples in spacetime have their own unique sound. The signal detected by LIGO from the neutron star collision known as GW 170817 was famously played as an audio chirper, a quick, rising frequency that culminated in a final, crashing tone, representing the final moments of the spiral and the moment of impact. It's the sound of two city-sized objects, each more massive than our Sun, meeting their end in a cataclysm that forges gold. This makes the abstract concept of a gravitational wave immediately visceral and understandable. Beyond their regular pulses, neutron stars can also sing through starquakes. Just like our own planet, the crust of a neutron star can fracture under tremendous strain, especially in magnetars with their unimaginably powerful magnetic fields. These starquakes release bursts of energy that cause the entire star to ring like a giant bell. These vibrations create oscillations in the star's spin rate and in the X-rays it emits, which can be translated into a low, resonating tone that slowly fades away. By studying the pitch and decay of this cosmic ringing, scientists can learn about the internal structure of the star, much like geologists learn about Earth's interior by studying seismic waves from earthquakes. The outreach value of these cosmic sounds cannot be overstated. Projects like NAS, a universe of learning, have created entire libraries of these sonifications, allowing people to experience the data in a completely new way. It makes the science accessible and emotionally resonant, transforming a complex astrophysical concept into something that can be felt. Hearing the rapid, steady heartbeat of a pulsar or the violent chirp of a merger creates a powerful, immediate connection to these distant phenomena, reminding us that the universe is not a static picture but a dynamic, evolving symphony of incredible forces. But all that gravity does far more than just bend light and trap matter. It warps the very fabric of time itself. This brings us to one of the most mind-bending consequences of Einstein's theory of general relativity, a phenomenon known as time dilation. Near a neutron star where gravity is hundreds of billions of times stronger than on Earth, time doesn't flow at the same rate as it does for us. From our distant perspective, a clock placed on the surface of a neutron star would appear to tick significantly slower than a clock here on Earth. It's not that the clock is broken. Time itself is literally stretched and slowed by the immense gravitational field. For an astronaut somehow orbiting just above the surface, hours might pass for them while decades or even centuries go by for everyone else in the universe. This isn't science fiction, it's a direct and measurable prediction of our most fundamental understanding of physics, and neutron stars provide the perfect extreme environment to put it to the test. We don't need to send a clock to a neutron star to observe this effect. The universe provides its own perfect timepiece, the pulsar's own spin. The incredibly regular pulses from these objects act as a finely tuned clock already in that extreme environment. As these pulses of radiation travel outward, fighting their way up through the neutron star's intense gravitational well, they lose energy. This loss of energy isn't in their speed. Light always travels at the same constant speed, but in their frequency. The waves get stretched, shifting toward the red end of the spectrum in a process called gravitational redshift. But this also applies to the timing of the pulses themselves. The interval between pulses appears ever so slightly longer to us, distant observers in a weaker gravitational field, than it would to someone hypothetically right next to the pulsar. This tiny, predictable delay in the arrival time of each pulse is a direct signature of time dilation, a whisper from the universe confirming that gravity doesn't just pull on objects, it pulls on time. The most precise tests of this phenomenon come from pulsars that are part of binary systems, especially those with another neutron star or a white dwarf. As these incredibly dense objects orbit each other, their pulses travel through gravitational fields of varying strength. When the pulse journeys from a point in the orbit where the gravity is strongest to our telescopes, the time dilation effect is at its maximum. When it comes from a part of the orbit with weaker gravity, the effect is minimized. By meticulously tracking these nanosecond-level changes in the pulse arrival times over years, astronomers can map out the gravitational landscape of the entire system. The results have spectacularly confirmed Einstein's predictions with a margin of error of less than 1%, making these binary pulsars some of the most stringent laboratories for testing general relativity ever discovered. This relativistic validation extends beyond just time dilation to other subtle effects predicted by Einstein, like the precession of the orbit itself. In the solar system, Mercury's orbit exhibits a slight wobble or precession that was partially explained by Newtonian gravity but fully accounted for by general relativity. In a binary system with two neutron stars, this effect is magnified thousands of times. The orbit isn't a static ellipse, it actually rotates over time like a spirograph drawing slowly turning. The rate of this precession can be colossal. In the famous double pulsar system Pulsar J0737-3039, the orbit precesses by an astonishing 4.2 degrees every single year. To put that in perspective, it took centuries for astronomers to measure Mercury's precession of just 43 arcseconds per century. Here, the effect is so dramatic it's unmistakable, and it again matches the predictions of general relativity with stunning accuracy. These observations do more than just confirm a century-old theory. They probe the very nature of spacetime itself. Every precise pulse from a distant neutron star is like a probe sent through the gravitational folds of the universe, reporting back on the exact shape and texture of reality. By listening to these cosmic rhythms and decoding the tiny delays and shifts, we are conducting experiments on a scale and in an environment that no human-made particle accelerator could ever replicate. Each confirmation of Einstein's equations in these extreme conditions gives us greater confidence that our understanding of gravity, from the gentle fall of an apple to the collision of entire galaxies, is built on a solid foundation, with neutron stars serving as the ultimate crucible for our theories. But what happens to these cosmic powerhouses over truly cosmic timescales? After the brilliant flash of their supernova birth and the energetic spin of their youth, neutron stars don't just vanish. They embark on an epic journey of cooling and fading that can span billions of years, eventually becoming some of the oldest objects in the entire universe. To find these ancient relics, we must look to the most ancient neighborhoods of our galaxy, the globular clusters. These are vast, spherical swarms of hundreds of thousands of stars, all bound together by gravity in a region of space only a few hundred light-years across. Crucially, globular clusters are like cosmic retirement communities. They contain some of the very first stars to have formed in the Milky Way, making them over 13 billion years old. It is within these dense, ancient stellar cities that we find neutron stars that have cooled into near-total darkness, their furious spins slowed to a near halt, and their brilliant X-ray emissions faded to a faint whisper. These elder neutron stars are profoundly different from the brilliant pulsars we often discuss. After hundreds of millions of years, their powerful magnetic fields have slowly decayed, weakening to a point where they can no longer generate those strong lighthouse beams of radiation. Their rapid spins have been braked by the emission of magnetic dipole radiation, slowing from hundreds of rotations per second down to perhaps one rotation every few seconds or even minutes. And most tellingly, they have cooled dramatically, having long ago shed the immense heat of their birth through neutrino emission. Their surface temperatures have plummeted from 1,000,000 degrees to perhaps only a few 100,000 degrees, making them incredibly faint and difficult to detect. They are the quiet, dark ghosts of their former selves, drifting silently through these ancient star clusters. Finding these faint objects is one of the greatest technical challenges in astronomy. Their primary signature is no longer a regular radio pulse, but an occasional, subtle flicker. Often, they reveal themselves only when they are in a binary system. If an ancient neutron star has a companion, its immense gravity can still pull material from that star, creating occasional bursts of X-rays that we can detect. These events, known as low-mass X-ray binary outbursts, act like a temporary flare, briefly illuminating the old neutron star and allowing us to pinpoint its location. In other cases, the Hubble Space Telescope has managed to directly image a handful of these cool, isolated neutron stars by their incredibly faint optical and ultraviolet glow, a monumental achievement akin to spotting a single candle flame on the moon. Studying these ancient objects is like finding a living fossil from the dawn of time. They provide an unparalleled window into the conditions of the early universe and the nature of the very first generations of stars, known as population 3 stars. The progenitor stars that created these oldest neutron stars were likely very different from the stars being born today. They were made almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang, devoid of the heavier elements that are ubiquitous in modern stars. This lack of metals profoundly affects how a star lives and dies, influencing its size, temperature, and the mechanics of its final supernova explosion. By measuring the properties of these ancient neutron stars, their masses and their spatial distribution within a globular cluster, we can work backwards to infer the properties of those first, long-vanished giant stars, understanding the initial building blocks of our galactic neighborhood. Furthermore, the sheer number of these ancient neutron stars in a globular cluster tells a fascinating story about the cluster's violent past. The extreme density of stars in a cluster's core makes stellar collisions and close encounters relatively common events over billions of years. These interactions can kick neutron stars out of the core or fling them into unusual binary systems, sculpting their current population. By censusing these faint remnants, astronomers can piece together the dynamic history of the cluster itself, understanding how it has evolved and interacted over the age of the universe. Each silent, cooling neutron star is a data point in a billion-year-old narrative of stellar life and death, making them invaluable relics for understanding not just the end of individual stars, but the grand evolutionary story of our cosmos. And just when we thought neutron stars couldn't get any more extreme, the universe presented us with one of its greatest modern mysteries: fast radio bursts. Imagine a flash of radio waves so powerful that it releases more energy in a single millisecond than our sun does in an entire month. For years, these events were complete enigmas, brief, incredibly bright blips of radiation detected from deep space with no clear explanation for their origin. They seemed to come from random directions in the sky, and their incredible brevity made them nearly impossible to pinpoint. Were they signals from advanced alien civilizations? Collisions between exotic theoretical objects, the theories were as wild as the bursts themselves. Then, in April 2020, a pivotal discovery finally brought neutron stars squarely into the picture, and it involved one of the most magnetically powerful objects we've ever encountered. The breakthrough came from a magnetar within our own galaxy, known as SGR 1935+215. This particular city-sized object, with a magnetic field a quadrillion times stronger than Earth's, had been known to science for some time due to its occasional, smaller outbursts of X-rays and gamma rays. But on that day, it did something unprecedented. It unleashed a simultaneous blast of both X-rays and an incredibly powerful fast radio burst. This was the smoking gun astronomers had been searching for. For the first time, a fast radio burst was directly linked to a specific known object, and that object was a neutron star in a state of extreme magnetic fury. The correlation was undeniable. The immense magnetic fields of magnetars were capable of producing these brilliant, millisecond duration radio flashes. So how does a magnetar actually create such a spectacular burst? The leading theory points directly to those intense starquakes we discussed earlier. Remember, the magnetic field of a magnetar is under unimaginable strain, wound tighter than any spring could possibly be. This stress periodically causes the neutron star's crust, a lattice of nuclei 100 billion times stronger than steel, to suddenly fracture and shift. When one of these starquakes occurs, it doesn't just create a little tremor, it violently shakes the magnetic field lines anchored to the crust. This sudden, catastrophic reconfiguration releases a colossal amount of magnetic energy almost instantaneously. This energy accelerates particles to nearly the speed of light, and as these particles interact with the surrounding magnetic field, they emit a massive, coherent beam of radio waves, a fast radio burst that can travel across the universe. But while magnetars explain a certain class of these events, they might not be the whole story. The incredible diversity of fast radio bursts suggests there could be multiple cosmic engines at work. Some bursts are one-off events, a single brilliant flash that never repeats. Others, known as repeating FRBs, fire off multiple bursts from the same location over days, months, or even years. This repeating behavior is harder to explain with a one-time cataclysmic event like a starquake. For these, astronomers are looking at other neutron star-related phenomena. One compelling idea involves a highly magnetized neutron star in a tight orbit with a massive, bloated companion star. As the neutron star plows through the dense stellar wind or circumstellar material of its partner, the immense shock waves generated could potentially power repeated bursts of radio emission each time it passes through a particularly dense clump of gas. Perhaps the most dramatic possibility involves the final act of two neutron stars. The merger of these ultra-dense objects, which we know produces gravitational waves and a kilonova explosion, could also be the catalyst for an incredibly powerful, one-off fast radio burst. The chaotic, energetic environment just milliseconds after the collision, with massive magnetic fields snapping and reconnecting and vast currents of plasma swirling, could easily generate a short, stupendously energetic radio blast. This theory is particularly appealing for explaining the non-repeating FRBs that seem to come from very distant galaxies, as a merger is a definitive single event in point. The study of fast radio bursts is a beautifully modern example of how astronomy works. It began with a complete mystery, anomalous signals that defied explanation. Through years of patient observation and the development of new, sensitive telescopes like CHIME in Canada, we gathered more data. Then, a single, crucial observation provided a key piece of the puzzle, linking them to neutron stars. Now, the field has exploded, with astronomers using FRBs not just as cosmic curiosities, but as powerful new tools. Because these bursts travel such vast distances, they act as probes, allowing scientists to measure the tenuous material between galaxies by seeing how the burst's different frequencies are dispersed on their journey to us. What started as a baffling signal has become both a fascinating product of neutron star physics and a unique new instrument for mapping the invisible structure of the cosmos. Given the extreme violence of a neutron star's birth, you might think that anything in its immediate vicinity would be utterly obliterated, and for the most part that's absolutely true. The supernova explosion that creates the neutron star is more than capable of vaporizing any existing planets that once orbited the progenitor star. Yet, against all odds, planets have been found in orbit around these cosmic powerhouses. This presents a fascinating puzzle. How do planets form in such a hostile environment, and what would it be like to live on one? The answer takes us to one of the most bizarre and extreme hypothetical habitats in the entire universe. The first planets ever discovered outside our solar system weren't found around a sun-like star. They were found orbiting a pulsar, a discovery that shocked the astronomical world. In 1992, astronomers studying the millisecond pulsar PSRB 1257+12 detected tiny, rhythmic variations in the timing of its pulses. These minuscule anomalies were caused by the gravitational tug of not one, but three orbiting planets, pulling the pulsar ever so slightly back and forth as they moved around it. This proved that planetary systems could not only survive a supernova cataclysm, but potentially form from the ashes of the destruction. The leading theory suggests that after the supernova, a disk of material debris from the shattered companion star or fallback material from the explosion itself could coalesce around the neutron star, providing the raw materials for a second generation of planets to be born from the ruin. Now imagine a world in such a system. The very definition of habitability would have to be completely rewritten. There would be no warm, nurturing sunlight. Instead, the entire sky would be dominated by the pulsar itself, a rapidly spinning, comparatively tiny object that would be the source of both light and unimaginable peril. This tiny sun would emit not a broad spectrum of light like our star, but a deadly, focused beam of radiation that sweeps across the planet with every rotation of the neutron star. For a brief moment during each sweep, the surface would be bathed in an intense flash of X-rays and gamma rays, capable of instantly sterilizing any unprotected life and shredding complex molecules. The periods between these beams would be plunged into a deep, frigid darkness, with temperatures plummeting to near absolute zero. The gravitational forces at play would be equally extreme, creating a world likely locked by tidal forces. Much like our moon always shows the same face to Earth, a planet orbiting a neutron star would probably have one hemisphere permanently facing its pulsar sun. This would create a planet of absolute extremes, one side a blazing hellscape periodically scoured by lethal radiation, the other a perpetually dark and frozen wasteland. The only potential sweet spot for any form of life would be in the narrow twilight zone along the terminator line between these two horrifying halves. But even there, survival would be a constant battle against the intense particle wind pouring from the pulsar, a relentless stream that would continually strip away any atmosphere the planet might try to hold onto. Beyond the radiation, the gravitational tides would warp the planet itself. The neutron star's immense gravity would squeeze and stretch the world, likely causing intense volcanic activity and global tectonic upheaval as its interior was constantly heated by friction. The very ground could be molten and unstable, a shifting landscape of rock and lava. For life to persist in such an environment, it would have to be nothing like anything we know on Earth. It might exist deep underground, protected by miles of rock from the radiation above, perhaps drawing sustenance from chemosynthesis using minerals heated by the tidal forces. Or it might be a form of life we cannot even conceive of, based on entirely different biochemistry, resistant to radiation and thriving in conditions of extreme pressure and temperature. While the discovery of pulsar planets expanded our understanding of where planets can exist, it also highlighted that the universe's definition of a habitat is far broader and far more terrifying than we ever imagined. From the cold, hard physics of their reality, neutron stars have also made a spectacular leap into the warmth of human imagination, becoming powerful and evocative fixtures in our science fiction and popular culture. Their inherent extremes, unimaginable density, deadly radiation, and crushing gravity make them the perfect backdrop for stories of adventure, danger, and the sheer awe of the cosmos. In many ways, these fictional portrayals, while taking creative liberties, serve as a critical gateway, translating complex astrophysics into relatable narratives that inspire a deep and lasting public fascination with the universe. Consider one of the most iconic and accurate depictions, the neutron star in Arthur C. Clarke's classic novel, Rendezvous with Rama. The story doesn't just use the star as a pretty backdrop, its physics are central to the plot. A massive, mysterious alien spacecraft is discovered on a trajectory that will use the neutron star's gravity to slingshot itself across the galaxy. The crew must unravel the ship's secrets before this celestial encounter, with the star's immense gravitational pull creating a literal and narrative deadline. This is hard science fiction at its best, using a real astronomical concept not as set dressing, but as a fundamental driver of the story, educating readers about gravity assists and extreme environments in the process. Video games, too, have embraced the terrifying potential of these objects. The popular space simulation game Elite Dangerous features explorable neutron stars and white dwarfs. Pilots can carefully navigate their intense jet cones, the focused beams of radiation pouring from the magnetic poles, to supercharge their ship's frame shift drive, allowing for hyperspace jumps that are vastly longer than normal. This neutron highway is a thrilling, high-risk, high-reward gameplay mechanic. Getting too close, however, means being torn apart by gravitational forces or cooked by radiation, a dire consequence that mirrors the very real dangers these objects pose. It's a fantastic example of gamifying real science, teaching players about magnetic fields and particle jets through immersive, interactive experience. Of course, creative license often takes precedence over strict scientific accuracy, and that's where some of the most fun and memorable portrayals emerge. The film The Core features a scene where a ship must navigate through a gigantic geode-like cavern inside a neutron star, while the real interior of a neutron star is a sea of exotic nuclear matter, not crystalline structures. The visual is undeniably striking and captures a sense of wonder about what might lie within these mysterious objects. Similarly, many space operas use neutron star guns or weapons that harness their power, playing on the public understanding that these are objects of immense, barely contained energy. These depictions, while fictional, reinforce the idea of neutron stars as the ultimate symbols of cosmic power. This cultural footprint extends beyond narrative to the very language of inspiration. The phrase neutron star itself has become a metaphor for incredible density, resilience, and focused intensity. We might describe a brilliantly compact piece of software as having the density of a neutron star, or a person's unwavering determination as neutron star grade. They represent the ultimate in nature's ability to compress and refine, a concept that resonates deeply on a human level. This metaphorical use spreads awareness far beyond the astronomy community, embedding these celestial wonders into our everyday lexicon. Ultimately, these cultural touchpoints are far more than just entertainment. They are a vital bridge between the esoteric world of astrophysics and the public curiosity that funds and supports it. A viewer who watches a spaceship brave the jets of a pulsar in a game or a movie is more likely to click on a news article about the discovery of a real millisecond pulsar. A reader captivated by Clarke's description of a gravitational slingshot might develop a lifelong passion for astronomy. By transforming data points into drama and scientific principles into plot devices, science fiction makes the universe accessible. It reminds us that these aren't just distant points of light or entries in a catalogue. They are places of unimaginable beauty and danger, waiting in the dark to ignite our sense of wonder and drive us to explore the real frontiers of science. Looking ahead, the next decade promises a revolution in our understanding of these cosmic powerhouses, thanks to a new generation of telescopes and missions specifically designed to probe their deepest secrets. Leading this charge is the Square Kilometre Array, or the SKA, an ambitious international project that will be the largest and most sensitive radio telescope ever built. Instead of one giant dish, the SKA will consist of thousands of individual antennae spread across two continents, South Africa and Australia, working in perfect harmony to create a collective collecting area of, you guessed it, a square kilometre. This colossal instrument will be so sensitive that it could detect an airport radar on a planet dozens of light years away, and it will turn its unprecedented power toward the skies to listen for pulsars. The SKA is expected to discover every single pulsar in the Milky Way that is beaming radio waves in our direction, potentially tens of thousands of them, including the faintest and most exotic varieties that have eluded our current technology. But its goals go far beyond just making a bigger catalogue. By monitoring these pulsars with exquisite precision, the SKA will function as the ultimate gravitational wave detector. It will use this galactic network of clocks to listen for the faint, low-frequency hum of gravitational waves produced by the mergers of supermassive black holes at the hearts of distant galaxies. This will open an entirely new window onto the cosmic symphony of these colossal events, helping us understand how galaxies themselves form and evolve over billions of years. Complementing the SKA's radio ears will be a new set of eyes designed to see the high-energy universe. The European Space Agency's Athena mission, the Advanced Telescope for High-Energy Astrophysics, is set to be the most powerful X-ray observatory ever flown. While current X-ray telescopes have given us stunning glimpses of neutron stars, Athena will provide a transformative leap in capability. Its huge mirror and advanced instruments will allow it to study the surfaces of neutron stars in incredible detail, mapping the hotspots created by particle bombardment and accretion with a clarity we can only dream of today. It will precisely measure the gravitational redshift of X-rays escaping from a neutron star's surface, providing a direct and ultra-precise measurement of the ratio between its mass and radius. This single data point is the holy grail for physicists, as it will finally tell us which equation of state is correct and definitively reveal the true nature of the exotic matter hidden within the core. Meanwhile, NASA's upcoming Nancy Grace Roman Space Telescope, with its incredibly wide field of view, will conduct vast surveys of the sky, likely discovering countless new X-ray binaries and other neutron star systems through their optical counterparts. And further on the horizon, concepts like a next-generation gravitational wave observatory in space, known as the Laser Interferometer Space Antenna or LISA, will be able to detect the mergers of neutron stars with stellar mass black holes, giving us a completely new perspective on these catastrophic events. Together, this fleet of new observatories will work in unison, using everything from radio waves and visible light to X-rays and gravitational waves to unravel the remaining mysteries of neutron stars, from the precise nature of their superfluid interiors to their role as the universe's primary source of heavy elements, bringing us closer than ever to understanding the ultimate limits of matter itself. Yet for all we've learned about these incredible objects, some of their most fundamental secrets remain locked away, challenging the very limits of our scientific understanding. One of the greatest unsolved puzzles lies deep within the star itself, the true nature of its core. We've theorized about exotic states like quark-gluon plasma and superfluids, but the reality is we simply don't know what matter looks like when crushed to densities beyond 100 million tons per cubic centimeter. This isn't just academic curiosity, it's a direct test of the standard model of particle physics. The core of a neutron star is a natural laboratory for conditions we could never hope to recreate on Earth, and deciphering its composition would reveal the fundamental rules that govern all matter under the most extreme pressure imaginable. Every new observation, from a massive neutron star to the gravitational waves of a merger, provides a crucial clue, helping us rule out some theoretical equations of state while bringing others into sharper focus. The origin of their unimaginably powerful magnetic fields is another profound mystery. We understand the basic amplification process during the supernova collapse, but why do some neutron stars become magnetars with fields 1,000 times stronger than ordinary pulsars? Is it simply a matter of the progenitor star's initial magnetic field and spin, or are there more complex dynamo processes at work during those first chaotic seconds of the collapse? Furthermore, why do these fields slowly decay over millions of years? The mechanism behind this magnetic fading is poorly understood, but it holds the key to understanding the electrical properties and conductivity of matter at these incredible densities. It's a cosmic detective story where the clues are written in the slow spin down of a pulsar and the sudden, violent outbursts of a magnetar. Then there are the enigmatic glitches, those sudden, tiny jumps in a pulsar's spin rate that happen without warning. Imagine a clock that has kept perfect time for decades suddenly gaining a few microseconds in a fraction of a second. The leading theory involves the interaction between the solid outer crust of the star and what is believed to be a superfluid neutron ocean in the interior. In this model, the superfluid rotates at a constant rate, while the solid crust gradually slows down due to the pulsar's braking radiation. Occasionally, the superfluid's vortices, which are usually pinned to the crust, suddenly unlock and transfer a massive amount of angular momentum to the surface, causing the observed spin-up. While this model is elegant, the precise trigger for this unpinning and the exact properties of the superfluid remain active areas of research, with each new glitch offering a tiny glimpse into the bizarre physics of the interior. These unanswered questions are far more than just gaps in a textbook. They are the very engines that drive modern astrophysics research forward. They challenge our most fundamental theories and force us to rethink the laws of physics. For instance, the detection of a neutron star with a mass significantly above 3 times that of the Sun would shatter our current models and might even point toward entirely new states of matter or exotic particles. Similarly, a deeper understanding of magnetar flares could reveal new aspects of quantum electrodynamics in the most powerful magnetic fields in the universe. These mysteries ensure that neutron stars remain at the forefront of astronomical discovery, with every new telescope and space mission designed in part to probe their secrets. They are the ultimate cosmic puzzles, reminding us that for every question we answer, the universe presents us with 10 more, each more fascinating than the last. This incredible precision in their rotation brings us to one of the most fascinating intersections of astrophysics and the search for extraterrestrial intelligence. For decades, scientists involved in SETI, the search for extraterrestrial intelligence, have scanned the cosmos for any signal that appears artificial, that breaks the natural patterns of the universe. And in that search, neutron stars have played a dual role, both as sources of incredible false alarms and as potential tools an advanced civilization might actually use. When Jocelyn Bell Burnell first detected the perfectly regular pulses of a pulsar, her team half-jokingly labeled it LGM for Little Green Men. It was a signal so artificially precise that it seemed it could only be the product of a conscious mind, a beacon. Of course, they soon found more, proving it was a natural phenomenon, but that initial moment of wonder highlights a key point. The pulses from a neutron star are, by their very nature, the most intelligible and predictable signals the universe produces. This has led some scientists to propose that if an advanced civilization wanted to communicate across the vast gulfs of interstellar space, manipulating a neutron star might be the ultimate way to do it. Imagine a technology so powerful it could somehow influence the spin or the magnetic field of a pulsar. A species wouldn't need to build a colossal transmitter from scratch. They could instead use a pre-existing cosmic lighthouse and simply modulate its beam, perhaps by placing a large object in a precise orbit around it to create a predictable pattern of eclipses or timing delays. This would be energy efficient on an unimaginable scale, harnessing the power of a star itself to send a message that could be detected across an entire galaxy. The message would be embedded in the timing of the pulses, a binary code written in the spin of a city-sized object. For SETI researchers, this means that when they analyze pulsar data, they aren't just looking for the natural rhythm. They are also quietly running algorithms to see if any pulsar's beat contains a hidden, intelligent pattern within its seemingly perfect natural clock. Beyond communication, neutron stars could also serve as the ultimate power source for a civilization far more advanced than our own. The concept of a Dyson sphere, a hypothetical megastructure built around a star to capture all of its energy output, is a staple of science fiction. But for a Type 2 or Type 3 civilization on the Kardashev scale, a standard star might not be enough. A neutron star, however, with its intense magnetic field and rapid rotation, represents an even more concentrated source of energy. The process of accretion, where matter is pulled from a companion star and heated to millions of degrees before impacting the surface, releases a tremendous flood of X-rays. An incredibly advanced society might learn to somehow harness this process, directly tapping into the gravitational and rotational energy of the neutron star to power their civilization. While this remains firmly in the realm of speculation, it encourages astronomers to look closely at neutron star systems that exhibit unusual or excess energy signatures that can't be easily explained by our current physical models. This also ties into the concept of neutron stars as natural navigation beacons for interstellar travel. We've already discussed how agencies like NASA are experimenting with pulsar timing for spacecraft navigation. It stands to reason that any species capable of crossing the light years between stars would have solved the problem of navigation, and using pulsars is an elegant, universal solution. Each pulsar has a unique signature based on its rotation period and location, creating a natural galactic positioning system. An interstellar spacecraft could triangulate its position by comparing the observed arrival times of pulses from several known neutron stars with a built-in catalog. Therefore, it's plausible that a network of pulsars near the galactic center or along potential interstellar highways would be of particular importance. If we were to ever find evidence that one particular region of the sky is being monitored by an artificial signal, it might be focused on a key navigational pulsar, a crossroads in the galaxy. Finally, neutron stars even influence astrobiological theories about where life might be able to exist. We traditionally think of a habitable zone as the region around a star where liquid water can exist on a planet's surface. But what about a planet orbiting a neutron star? As we discussed, the environment would be incredibly hostile, bathed in periodic blasts of lethal radiation. However, life is tenacious and might find a way in the most unexpected places. If a planet had a sufficiently thick atmosphere or a global ocean with a miles-thick ice crust, it could potentially shield any life forms deep below from the radiation. The energy source wouldn't be sunlight, but the tidal heating generated by the neutron star's gravity constantly flexing the planet's interior. Entire ecosystems could theoretically thrive around hydrothermal vents on the ocean floor, completely independent of the deadly drama playing out in the sky above. While it's a long shot, considering these extreme scenarios expands our understanding of life's potential and ensures our search for it is as broad and creative as the universe itself. Yet even these silent, cold orbs will not last forever. The ultimate fate of a neutron star is tied to the grandest timeline of all, one that stretches far beyond the lives of stars, galaxies, or even the era of black holes. Over timescales that are almost impossible to comprehend, trillions upon trillions of years, the protons and neutrons that make up a neutron star's incredibly dense structure may not be stable. Some theories in particle physics suggest that protons themselves have a half-life, a point at which they will spontaneously decay. If this is true, then over a period of time around 10 to the 34 years, a neutron star would very, very slowly evaporate, its matter transforming into energy and lighter particles, fading away into the darkness of an ever-expanding and cooling universe. This leads to the most profound and silent ending imaginable. If protons are stable and do not decay, then the neutron star's journey ends as a black dwarf. But this is no ordinary stellar corpse. All of its particles would have long since settled into their absolute lowest energy state, forming a perfect crystalline lattice. It would be a single, incredibly massive sphere of iron-like matter, hovering just a fraction of a degree above absolute zero. It would be utterly dark, emitting no light, no heat, no radiation of any kind. It would be a fossil in the purest sense, a monument to a universe that was once vibrant and full of energy, now drifting silently in a cosmos that has reached a state of maximum entropy, a lukewarm sea of diluted photons and stray particles. In this unimaginably distant future, the neutron star would be one of the last recognizable structures in the entire universe, a final testament to the age of stars. Their story, from their violent birth in a supernova to their silent fate as black dwarfs or their dramatic end in a merger, cements their role as fundamental characters in the life cycle of the cosmos. They are not merely endpoints, they are crucial transformers. They take the simple elements forged in the Big Bang and in the cores of living stars, and through their spectacular lives and deaths, they create the heaviest elements that make rocky planets and life itself possible. They enrich the galaxy, regulate star formation, and provide the tools to test the very laws of physics. In their silence, they become the universe's ultimate historians, their cooled surfaces potentially preserving information about the conditions of their birth in ways we are only beginning to imagine. To study a neutron star is to understand the universe's past, but it is also to glimpse its far, far future, a future of deepening cold and stillness, where these ultra-dense relics will be the last sentinels of a brilliant and dynamic era that once was. From their mind-bending density, where a single teaspoon weighs as much as a mountain, to their role as the universe's ultimate alchemists, forging gold and platinum in violent kilonova explosions, neutron stars have proven to be far more than just cosmic curiosities. We've journeyed through 30 astonishing facts, uncovering how these city-sized powerhouses are born in the most violent stellar explosions, spin faster than a kitchen blender, and possess magnetic fields so strong they could wipe a hard drive from half the distance to the moon. They serve as nature's most precise clocks, allowing us to test Einstein's theories with unparalleled accuracy, and as gravitational wave detectors, listening to the hum of colliding supermassive black holes. They might even hold the key to detecting dark matter, acting as cosmic sentinels in the dark. These distant beacons are the ultimate cosmic laboratories, pushing matter to its absolute limit and revealing states we can only dream of creating on Earth, from nuclear pasta stronger than any known substance to the quark-gluon plasma that hasn't existed since the Big Bang. They shape their galaxies, regulate star formation, and their final mergers seed the cosmos with the very elements that make up our world and our bodies. Their story is a profound reminder that the universe is a place of dynamic, violent beauty, where the laws of physics are written in extremes. If your mind is as captivated by these cosmic powerhouses as ours is, we'd love to hear which fact amazed you the most. Was it the Black Widow pulsar vaporizing its companion, or the incredible idea of a future spacecraft using pulsars to navigate the galaxy? Share your favorite neutron star moment in the comments below. Let's keep the conversation stellar. For more deep dives into the universe's greatest mysteries, make sure to subscribe and hit the bell so you don't miss our next journey across the cosmos. Until then, keep looking up and wondering about the incredible secrets waiting in